We've reached the part of the semester where we are going to spend some time actually constructing a device that is not just one type of junction. So all we've covered up till now is kind of just one junction, a PN junction, a metal semiconductor junction, that kind of thing. And now what we're going to do is look at what happens when you put something between the metal and the semiconductor, and we're going to end up putting together one of the most common transistors that's being used today. So first of all, we're going to start out talking about capacitance, which you probably know about, but capacitance occurs anytime you have a separation of positive and negative charges. Capacitance depends on how far apart the charges are, what's between them, so what kind of material is between the separated charges and the cross-sectional area. We use the permittivity of the stuff between the charges to help determine what the capacitance is. So given that, we're going to look at a metal oxide semiconductor structure. So we're going to start out where we have a semiconductor substrate. It can be P-type or it can be N-type. And attached to that is an insulator of some type. Usually we use some kind of silicon dioxide. But at the top you'll see there's just a black bar, and that is some type of metal. It can be some other type of polycrystalline silicon, but basically it's always called a metal. So when we look at this structure, if we can get a situation where there are charges separated between the semiconductor and the metal, then we would have a capacitance, because the thickness of the oxide gives us the distance between the two charge separations, and then the permittivity of the oxide tells us how to do the capacitance. Generally, what we calculate is actually a capacitance per unit area, because we don't always know what the area is. So we calculate a capacitance per unit area, and then we can take that and associate it later to an area if we have to. So the first thing we're going to look at is a P-type substrate. So there's P-type material as the semiconductor, and then we have some type of insulator and then the metal. And we are attaching a voltage source such that the metal side is negative. So there's actually a negative charge connected to the metal and a positive charge connected to the semiconductor. And then what happens is, as we increase the voltage, so as we make the voltage more positive, the holes in the P-type material are pushed up towards the end of the semiconductor, towards the junction between that and the oxide, and then we get negative charges in the metal and we get an electric field. All of that goes together, and what we end up with is an accumulation layer of holes that basically look like positive charges. And since they look like positive charges, and then there's negative charges at the other end, and we have a separation of charges, as you can see, we do have a capacitance. Now, if we take the polarity and reverse it, something else happens. If we reverse the polarity of the voltage, and now the metal end would be positive, and the semiconductor at the bottom end would be negative, well, what happens in that case is the holes are drawn to the negative end, and there is a depletion region that actually gets induced at the place where the semiconductor and the oxide meet. So there's actually a space charge or depletion region now at that junction. So what will happen is we'll end up with a positive charge at the top, and then we actually have a space charge region that can be used. And as you might guess, that space charge region has a particular width, which is going to be used in figuring out the parameters of the MOS capacitor later. So that is an important parameter that we're going to have to use, which we've already done. We've already calculated distances of space charge regions into N-type or P-type material, so this is not really different. This is just a different application of it. So we're going to look at the energy band diagrams because you all know that I love energy band diagrams and they do illustrate what's going on. So if we look at just a MOS connection that's not doing anything, so basically it is at zero bias and there is no energy being put into the system, so we're just looking at nothing, basically. We just have the Fermi energy down near the valence band, which is what we expect because it's P-type material, so that's good. Now, if we go ahead and apply a negative voltage, when we do that, the energy bands, except for the Fermi energy, will bend upward. They'll get pushed upward a bit, and so there'll actually be holes that accumulate down in the valence band right at that junction point. If we turn the voltage around and we apply a positive voltage, then the bands bend the other way. Now, if they're bending the other way, then the Fermi energy is moving farther away from the valence band. And that means the actual structure of the material is changing right at that point. There is a space charge region, and that's the one that was induced because we had applied voltage to the other illustration that was done. But you can imagine that if we apply more voltage, we would have a larger space charge region, and also the bands would bend further downwards, which is indeed what happens. And what we get at the very junction between the semiconductor and the oxide, we actually get a material that looks N-type because there's electrons and the conduction energy is closest to the Fermi energy right at that point. So we end up with actually an N-type at the boundary between the semiconductor and the oxide, and P-type in the semiconductor in the bulk. And there is, again, a certain distance to this space charge region, and we'll look at how to calculate that in a little bit. If we have a different type of material, if we started with N-type instead of P-type, basically everything is going to happen the same. So I'm going to go through these kind of quickly because it's pretty much the same idea, but just to let you see what exactly happens. So this time we have electrons that are in the N-type material, and we apply voltage so that the metal side is positive, and when we do that, the electrons are attracted to the oxide layer, and you get this accumulation layer of electrons. If we return the voltage around and we do it again, then the electrons are pushed, and you get an electric field and a space charge region just like you did with the P-type material. The space charge region has a distance. Again, everything else is the same. And then when the energy bands bend, they also go in the opposite direction. So we get an accumulation layer of electrons when the positive voltage is applied. And then when we do negative voltage, we get the bands bending upwards, and we get a space charge region. And then at a large negative voltage, we end up with the maximal space charge region, and we have an inversion layer of holes. So again, we have P-type at the boundary between the semiconductor and the oxide, and then we have N-type in the bulk semiconductor, and the transition goes through that space charge region just like in the P-type substrate. So the thing that we need to know is we need to know how to find the width of that particular space charge region, because that's going to be used to find the capacitance per square centimeter. So we need to figure that out. And it only extends into the semiconductor material. It doesn't go into the oxide. So it's basically found the same way we did a one-sided PN junction just a couple lectures back. So This is kind of a complicated process because we do know how to calculate widths, but we actually have to find the proper work functions to make it work, because it's not exactly the same as when we're dealing with just semiconductor material. When we dealt with that, we could find the differences between the two because they were both semiconductor materials. And now that we're looking at the difference between a metal and a semiconductor, that's going to be a little bit different. So it's going to be a little bit different process. So first of all, the first thing we're going to do is we're going to look at the relationship between how the semiconductor work function in the bulk part works differently than the work function at the interface between where the semiconductor connects to the oxide. So the value phi sub Fp, that's the potential difference between the intrinsic and the Fermi energy in the bulk semiconductor material. So what we started with P material, and that is the energy difference. That is something that we calculated before early on in the course when you did EF minus EFI to find the difference, or EFI minus EF, depending on if you were looking at N-type or P-type material. That's the calculation you did. So it's the same thing, it's just denoted differently. The other work function is at the interface, and that is basically how much the intrinsic Fermi energy changes between the bulk material and the interface. And actually, it's going to be the same as the drop in conduction energy or valence energy, but it's just depicted in the middle. So that's how we look at it. So again, we can calculate the work function in the bulk material. That's easy. We've already done that. But we can't really find the work function at the interface just yet. We will be able to, but not quite yet. First of all, in looking at the depletion region width, remember when we were looking at the one-sided p-n junction, and we used this relationship in order to determine the value of the width of the depletion region. And remember that we added those voltages together, and basically that value is going to be the total potential change through the pre-n junction. And that's the same as that phi sub S in the MOS capacitor. So that's the potential change through the oxide, basically, because of the connection. So that's what we need. So if we change that just a little bit, we change that to this equation, which is almost the same. We're just using different symbols to represent the potential change. That's the only real difference, and we're going to find it differently. How are we going to find phi sub S? Well, what we're going to do, we're going to cheat just a little bit. We're going to cheat because we're going to set it equal to something that we can find. And it turns out that this is actually a very important thing we can set it equal to. So what we're going to do, we're going to set it equal to twice the work function in the bulk material. And we can calculate that. That is actually known as the threshold inversion point. And if you apply that voltage to the gate of the MOS capacitor, that's the end that has the metal on it, you will actually have that maximal space charge width. And things will happen when you apply the threshold voltage later. We will talk about threshold voltage with respect to MOS capacitors, and then we will talk about it again with respect to MOSFETs, but it's the same idea. So there is a particular voltage that if we apply it to the gate, we get the conditions that we want, and in this condition, that work function is actually equal to twice what it is in the bulk material. So when we do that, we can actually calculate and relate those values to each other and then put them in the equation that we already know how to use. So now, when we apply the threshold voltage, that means that the conditions exist such that the work function at the surface is equal to twice the work function in the bulk material, and the depletion region is its maximum width. And that way, we can just substitute in 2 times the work function of the bulk material, which makes our equation 4 times the semiconductor permittivity, which remember is a combination of material and the permittivity of free space, and then the work function of the bulk material divided by the charge of an electron times the acceptor concentration. And again, we can calculate the work function in the bulk material very easily. Also remember that V sub little t is that value 0.0259 volts, that we can use that as a constant, and you can use it for the rest of the course as a constant because we're not going to change the temperature anymore. So you can just remember that number and use it, and it will make your calculations a little bit easier. So that's in P material. N material, it's almost exactly the same. In fact, it is pretty much exactly the same. The only thing that changed is now the work function is an F sub N. The carriers are donors rather than acceptors, and that's it. Everything else is the same for that. So now that we know how to find the depletion region width, we're going to go on and we're going to look at how to find the work function difference between the metal and the semiconductor. So that'll be the next thing we look at.